Hi, everybody. I'm Tyler Setterly. I'm a senior research scientist here at UW, and I'm really happy to have this Hack Week again. I'm here to present information with Deputy Project Scientist for ICESat-2, Nathan Kurtz, and this is using material from Tom Newman at NASA Goddard, Ben Smith from here at UW, collaborators, science team members, slide team members, and product leads. So ICESat-2. ICESat-2 is NASA's current polar orbiting satellite altimeter. Its main project objectives is to improve estimates of ice sheet volume, mass, sea level contributions, to be able to recognize the signatures which are causing those changes, estimate sea ice thickness in order to get into the energy exchanges of our planet between the atmosphere, ocean, and ice, and also to measure vegetation height by having continuous measurements of biomass, both forest and ecosystem. The primary instrument on ICESat-2 is ATLAS, the Advanced Topographic Laser Altimeter System. It is a 10 kilohertz micropulse LiDAR. It fires 10,000 shots per second, and this laser is split into 6 beams. 3 weak beams, 3 strong beams. And detectors on ICESat-2 are sensitive to single photons. That is pretty much picosecond detection is very cool. We have 3 beam pairs separated by 3 kilometers in order to increase the spatial coverage. That's very important for biomass so that we can try and get as much as possible. And each beam pair has beams separated by 90 meters. That way you can separate a cross-track slope instantaneously. The 2 different beam energies allow us to have enough of a dynamic range to measure very dark targets with the strong beam and very bright targets with the weak beam. But the strong beam also works very well on very bright surfaces. The sort of pattern of what the beams make is this rectangle that would go through time, measuring things in these sort of lines. The transmitter on ATLAS has a single working laser at a time. We're still on the primary laser. This goes through some optics to reach the laser sampling assembly. Some small amount of laser energy goes to the start pulse detector. That starts our stopwatch. So everything is going to be in reference to that. Some more energy goes through what we call the transmit echo path, or TEP. This goes to the receiver assembly, and this allows us to look at things like the transmit waveform and see the health of the instrument. The major percentage of the laser energy goes through some shaping optics where the beam gets a little bit wider, it gets steered towards the planet, and then it's split into the 6 beams, 3 weak, 3 strong. On the receive side, some of these lasers are going to bounce off the planet and come back to the telescope. We're also going to get a lot of solar radiation just as the sun emits light. But the telescope has a very narrow field of view. This is to try and limit the amount of solar radiation that goes into the satellite, and it's also to try and prevent multipathing, where the laser beam hits off something, hits on something else, hits on something else, and then returns to the satellite. So we'd have a narrow field of view to try and make it so we just get one single return from the light. Light then goes through this meandering path to an optical filter. This removes the bulk of the lights that's not 532 nanometers, so we really focus down into green, but the sun emits a lot of green light, so we're still going to have a lot of background. This is also where that TEP stuff comes in directly from the transmitter. This allows us to measure, again, like the waveform shape, see on the health of the instrument, and allow us to compute corrections. After that, it's into the detectors. ICESat-2 uses photomultiplier tubes, or PMTs, to measure laser light and try and get the timing on the returns. For the strong beam, it's 4 times stronger than the weak beam, and we have a 4x4 array. This light is evenly spread over that 4x4 array, and out of the 100 trillion photons that leave the instrument, about 10 return for every given shot. So we're losing a lot, but for most of the time, we're getting about 7 to 10, so we're not using all the detectors at any given time. For a very bright or specular surface, we can get more photons returning. This can lead to saturating the detector and thus not being able to detect more photons at that time. When that happens, the height can be biased towards the first photons that return. And so if you're using the photon level data, it's important to keep in mind that the height that you might be detecting is a little bit biased up because of this first photon bias. And this is common for all photon counting LiDARs. For the weak beam, we have 2 by 2 pixels grouped together. But because the laser is 4 times weaker, we're not expecting to saturate those detectors as much. And then it goes into the timing channels. That is one piece of information. That gives you the photon time of flight from when we click the start watch and when we get it back. The other pieces of information you need to get latitude, longitude, and height is where that satellite is in space, which we use with GPS, and that is processed by the geodesy group at NASA Goddard. And then what we do is we verify our orbit estimates using satellite laser ranging. So there's stations on Earth that fire a laser at a laser retroreflector on the satellite, and we measure where we think it is, and we compare our orbits with time. The other piece of information we need is where we're pointing. So if we had a flashlight, we could know where we are, but we want to know where that flashlight is pointing. And so there we have cameras on the other side of the satellite that look out towards space and allows us to look at the orientation of everything in space. That combined with a reference system of knowing how the telescope is pointed in reference to the star cameras gives us where we're pointing. And then we compare that data with retroreflectors on the ground that are about the size of your pinky fingernail so that we can verify that our pointing solutions are good. So time of flight, where the satellite is, where we're pointing, we can get a photon return and its geolocation. So latitude, longitude, height, and any given time. This is sort of a schematic showing the same thing. We have Atlas firing a laser at that elevation next to the Penguin. And then we're verifying that, we're getting the location of the satellite with GPS, verifying it with the SLR, and then we have the Atlas pointing system, which is a combination of the star cameras and its internal laser reference system. And that gives us, through some swizzling, the elevation. ICESat-2 data production goes through this sort of process, going from the engineering data that's telemetered down from Atlas. This is bound in compressed format. ICESat-2 can only telemeter down some packets of data. So it's not going to telemeter down every single photon over the entire width of the atmosphere. It's going to do some onboard cutting down to get it to where I think the surface is here. I'm going to give you this packet of photons. That telemeter data gets repackaged into HDF5, which is a common format we will go through a lot this week. That's the ATL01 data. Then a bunch of corrections are applied and calibrations. That gets us into some scientific units for time of flight. Adding in the orbit determination, the pointing gets us to the long track data, level 2. That's everyone's favorite ATL03 geolocated photons. From there, more swizzling. You can take the photons and do some sort of averaging, whether it's using like a set length or set number of photons to get some sort of science and long track data. This could be like for land ice, sea ice, oceans, land vegetation, or inland water. And then on top of that, you can do more swizzling from your science long track data to create some sort of gridded data or combined data, such as the gridded products. Some stuff to know is any piece of software that's used to create any of this data is part of ASAS, the Atlas Science Algorithm System. That gets combined for every single product into a PGE. It's like a bundle or a container almost of like, this product is generated with this PGE. This is all part of the science investigator-led processing system. Oh, yeah. That's something that my postdoc advisor, Tom Newman, used to like combine in some
Do science magic with. Okay.
black box. Yeah. Yeah, this is all part of SIPS. And then if you want to make targets of opportunity requests or look at the PG software, you can do that at the Science Computing Facility, which is at NASA Goddard. The big product chart, so this is the same chart, but now it's broken up into all the different pieces. We have ATLO0, the stuff that's telemetered down, ATLO1, where it's repackaged into HDF5, ATLO2, where it's converted into science units, adding in the pointing and the orbit determination to get geolocated photons, and then the level 3A, land ice, sea ice freeboard, land vegetation height, ocean surface height, inland water, and then a future product is bathymetry for coastal and lake bathymetry. Why would you use the science along track versus ATLO3 for three? You do it for three reasons. One, ATLO3 is huge. It's over 300 terabytes. And before surfaces like slide rule that simplified using ATLO3, it was unwieldy. And for the first 2 years of the mission, the data was not on S3, and so you had to get it from NSIDC directly, which took a long time because if you want to do something at scale, trying to transfer 300 terabytes, it's going to take some time. The other reason is that ATLO3 can give you flags for signal confidence, like this is probably a good photon, it's probably not background, but it doesn't tell you the surface. And so if you want to determine the surface, you have to do some algorithm to figure out where the surface is. All that stuff is done in the along track science products. It's devised by a lot of smart people to try and lock down on surface of interest. The third is that there's corrections applied, such that first photon bias, to try and make it so this is actually where the surface is and not biased because I'm on a bright surface and we saturated the detectors. Below that are the combined products for land ice. That's ATL11, which takes all the along track data and gives you a nice thing that you can compare through time. And then there's two gridded products, 14 and 15. For sea ice, there's two gridded products, gridded sea ice freeboard, and then they also use the data where they have leads to get polar ocean surface height. There's going to be a gridded product for land veg. That's in progress. There's gridded ocean topography, and then that's at a monthly time scale. And then there's a 3-month one that fills in even more on the ocean. And then there's mean inland water height, whereas if you have any lake, they give you sort of one average thing for that lake. So I think there's 1 million different lakes that ICESat-2 is trying to track, and it'll give you something if ICESat-2 hit that at any given time. And then there's the atmosphere products, which have a level 2, a level 3A. The level 3A ATL09 is used in a lot of products to determine, am I affected by clouds here? Were there clouds above me, and is my surface affected by that? But it also is used for things like measuring clouds, measuring blowing snow, measuring dustiness, smokiness, things like that. And they come in also weekly and monthly products. This is the exact same chart, but it's now colored by discipline: land ice, sea ice, veg, ocean, coastal, inland water, and atmosphere. ICESat-2 flies at 500 kilometers altitude. It has a 92-degree inclination that gives us data from 88 degrees south to 88 degrees north, and it does an orbit 15 times a day. It's following 1,387 repeat ground tracks, so it's trying to point to the same spots on the ground, these same predefined 1,387 tracks. And 15 revs per day and 1,387 means that you complete a cycle every 91 days. After that 91 days, it starts back again at RGT1, and then it does it again. And that's the next cycle. So you have a different way of defining things in time and space by both date and latitude, longitude. You can also define it by orbital, RGT, and cycle. And all these RGTs are available in KML form at the ICESat-2 website for both prior ground tracks and future predicted. ATL03 would be enormous if we did an entire orbit. Each one right now is something like 4 gigabytes, but if we had the entire orbit, it'd be something like 50 to 70 gigabytes per file. That's unwieldy. And so we break up ATL03 into 14 granule regions, which are set up like this. This simplifies the size of the files so that you can actually download them. And it makes it so if you were only interested in, say, Antarctica, you only have to get regions 10, 11, and 12 versus an entire enormous granule. So it simplifies the calculation of the higher order products that as well. This is the same thing, but I like looking at polar maps. This is in polar stereographic. So you can see where region 11 ends and region 4 ends with these maps. Okay, ICESat-2 samples in a long track manner. It has 3 beam pairs, each one separated by a little over 3 kilometers, and each beam pair has 2 beams separated by 90 meters. Again, the 90 meter separation between beams is to get instantaneous across track slope when it's pretty much cloud free. And then the between the beam pairs is to increase spatial coverage. At any given time, we may be in one orientation or the other. There's a sailboat mode and there's an airplane mode. And this is to maximize the solar input to the solar arrays. And so when the orbit is one part in its quote unquote beta angle, it's in one mode. And if it's not getting enough solar radiation, it's in the other mode. And so any given ground track could be a weak beam or a strong beam, depending on the orientation. And so that's something to check on when you download a file. And which beam am I looking at? Am I looking at a strong beam or am I looking at a weak beam? The files have a pretty common naming convention. This is for anything that's in a long track and not sea ice. There's the product numbers such as ATL03. And then there's the date, year, month, day, hour, minute, second, and the seconds are in UTC seconds of when at the very start of that file. Then you have the RGT, which ranges from 1 to 1387. The orbital cycle, so that 91-day period. So at the very beginning of the mission in 2018, we're on cycle 1. And right now, cycle 20? Something like that. We're almost in cycle 20, cycle 19, or something like that. Then you have that granule number, 1 to 14, the data version and the data release. Our current data release is release 6 for HLO3, 6, 7. Sea ice is a little bit different. For sea ice, we only have 2 granules per track. We have a northern hemisphere granule and a southern hemisphere granule, and that's denoted by this hemisphere flag. And then that granule number for all sea ice is 1. So it's slightly different, but very similar. All right, data. This is ATL03. It's a track I really like looking at. This is over Thwaites Glacier. It's a very messy one. That's why I like looking at it, because it's good for demo. In ATL03, you have every single photon that's telemetered back and every single parameter that you could use to derive some of the higher level products. So you have geolocation, time, elevation for every satellite that's telemetered down. You have photon classifications. Do I think that this photon is signal, or do I think it's from the sun? You have geophysical and atmospheric corrections, so you can correct for tides or various other ocean corrections. And then you have a bunch of instrument parameters so that you can try and derive some sub-centimeter corrections, such as the first photon bias. But it's huge. It's over 300 terabytes, so it's kind of unwieldy. And you might not need to have that level of precision to do your science. But if you're looking at scales that are very fine, you might want to be in ATL03. The plots that we're looking at, again, they're pretty complicated. At the top one, this is using the internal signal classifications, whether it's background, so that's from the sun, low confidence, medium confidence, or high confidence. Most of that high confidence over this land is all together, so it's really hard to tell it. And there's a lot of high confidence photons because it's a very bright surface. Red is that TEP beam, that transmit echo pulse beam. That's not actual stuff from the surface. That's internal photons from within the product. So it's going from the transmitter to the receiver. For release 6, there's a brand new way of weighting photons called YAPC. This gives you photon weights. This uses a clustering algorithm to try and determine how strong of a signal anything is. And so this is really cool if you're looking at stuff that's like in between products, like for icebergs or low clouds, as this just tells you, hey, I think this is something cool because it's close to a bunch of other photons. But you do need to remove TEP beams or stuff that's instrument biases, as they can be weighted like, oh, this is close to a bunch of photons, but it's not an actual geophysical surface, it's a tap beam. And there's a bunch of surfaces like slide rule that really make it quick to work with ATL03 data, which is something that we didn't really have at the beginning of the mission. Another channel of data that's transmitted back is for the atmosphere products. This gives you backscatter. So this, instead of just being the telemetered photons close to the surface, this gives you stuff that's much higher up. And so you can derive stuff like high clouds, blowing snow, smoke, fog. And it's also used to mask out or determine if you're affected by clouds in your ground return. So if you are looking at something and something looks weird, you might want to look at ATL09 to make sure that you're not affected by clouds. And then there's gridded products for these two. All right. First of the land ice science products, ATL06. ATL06 takes 40 meters of photons in the along track direction and then fits a line to it. It's a slopey line, so it can be not just flat, it can have some sort of tilt to it. And then it windows down on those photons to try and get the surface. But it keeps the window wide enough so it tries to get the full shape of the transmit pulse, or the full shape of the received pulse. And you want to know how the transmit pulse is affected by things like the slope and the surface roughness, and so that's why you want that full window. We also get height errors through that surface fit, and we apply those sub-centimeter corrections for first photon bias, and the shape of the transmit pulse is not purely Gaussian, it has a little bit of a tail, and so there's a transmit pulse shape correction there as well. It's a great product. It's a lot lighter than ATL03. It's great for land ice applications, but if you're looking at stuff that's finer than 40 meters, you might need to look at ATL03 first. But for a lot of things, 40 meters is great. And so if you're looking at elevation change or anything to do with the surface of the ice sheet, that's great. The other caveat is ATL06, and Philip, wherever he is, will know this quite well, is only designed for single surfaces. So if you have a melt pond and you want to get the bathymetry of the melt pond, you break ATL06's warranty. It's not built for that. Taking away everything you need. Yeah, but it's a great product. On top of that is ATL11, which combines all the data from all cycles into a single granule. So here you can make easy measurements of elevation change through a single file that you download. It's smaller than ATL06. We're looking at 120 meter long track segments instead of 40. But you can look at things like this picture is a grounding zone. So this is where the ice actually flexes due to tides. And so you can look at elevation change, you can use crossovers that are in the product, and it has all those sub-centimeter corrections applied. It doesn't work great in heavily crevassed areas, as 120 meters is somewhat coarse if you're at a spot that's heavily crevassed and chopped up into a million pieces. And so if you're looking at those regions, you might want to go to something else. But if you're wanting to measure elevation change, especially at a single track, ATL03 is amazing. We take all ATL11s for glaciers and ice sheets where there's repeat track measurements, and we create two products from that, ATL14 and ATL15. ATL14 is like a static DEM. It's time tagged to 2020. ATL15 is quarterly to multi-annual estimates of the elevation change, and it's a grid. And so it simplifies if you're wanting to use a grid for your ice sheet model, if you're wanting to do volume or mass change estimates from ICESat-2, or if you wanted to extract a transect, like if you're going to be doing a field campaign, you can extract a transect that doesn't follow a long track segment. You can just draw it anywhere. The problem is it's a model. And so where you don't have data, the model is going to degrade. And so ATL14 is not great where you don't have data. And quarter annual sampling might not be high enough for you. But this is investigating some of the things you can do with ATL-15, you can just draw a transect. This is in Greenland from Yakutshaven, and you can see what the height changes as a function time. So Yakutshaven between 2018 and 2022, near the front, lost almost 30 meters. And you can do that everywhere. So you can take your point of interest and you can extract a time series. Another of the along track science data is ATL-08. ATL-08 uses a different type of extracting photons, which is decomposition using like a pseudo histogram. It bunches them all into bins, and then you can try to partition different peaks in that waveform. This is through a piece of software called Dragon that is developed at the University of Texas. And a really great thing about that is you can get the ground, you can get canopy, you can get the top of canopy, and using the same sort of algorithm but flipped upside down, you can get the top of a lake, and you can try and get bathymetry if you know the optical properties of the water. ATL-08 includes all these photon classifications, so this is not a confidence level. Yeah. Okay. ATL-08 includes all those photon level classifications, so you can take them and apply it to ATL-03. And services like Slide Rule let you do this really easily, as Slide Rule can read ATL-08 photon classifications and apply it to the ATL-03 level.
Did that answer your question? Yeah. Yeah.
Cool.
Okay. Hey, Tyler, quick check-in on time. We have about 20 minutes left. I wanted to see if you.
I'll be good.
Okay.
Yeah.
And
I know
Nathan's,
everyone wants to get to lunch.
but Nathan's part is coming into this as well.
Soon.
Okay, great. Thanks.
Yeah. Coming soon is gridded products from the land veg, and they're working on using Slide Rule and machine learning to create a brand new global vegetation product, but this is work in progress and will probably be next year. Other product last one that I will talk about is the ocean product. There's ATL-12 that takes photons and averages it over 7 kilometers. The 7 kilometer averaging length is to beat down the effects of individual waves. ICESat-2 can see waves, and so if you're treating it as a flat surface, that stuff's going to be counted as error. So it averages over 7 kilometers to try and get the really fine accuracies. ATL-12 is great for deriving a dynamic topography, sea level rise along these segments. And then there are gridded products, ATL-19 and 23, that fill in and create global maps of sea surface change from ICESat-2. And with this, we're going to switch over to Nathan, who will talk about sea ice products and the future state of the mission.
All right, thanks, Tyler. All right, can people hear me? Online? Okay, so I'm Nathan Kurtz. I'm the Deputy Project Scientist for ICESat-2. I'm also the sea ice product lead, so I'm going to do a little bit of talking on the sea ice products, but then, where are we with the future of the mission? We just went through the senior review process, and so, what does the outlook for the mission look like? But continuing on the vein of what Tyler was talking about with products, for sea ice, there are several different products. So there's the along track products. So this is ATL-07. This is the surface height. And so what this is doing, it's aggregating 150 photons along track. So it's trying to retrieve a surface height from that. It does this by convolving a transmit pulse with a Gaussian fit, doing corrections like first photon bias, and then trying to retrieve a height. So the advantage is that this is, again, a lighter product than ATL-03. It's very accurate, so we've done a lot of work to verify the accuracy. It gives you ancillary information like surface roughness, things like that. But it's sort of a variable length scale. Some people really don't like that, especially if you're looking at something like a sea ice ridge, which is at a much finer length scale. And some of the surface flight type flagging in ATL07, it's not well developed. It's sort of like a preliminary, this might be a sea ice lead or something like that. And that's more developed in ATL10. I would suggest to use ATL07 if you're looking at, just what are the base level surface heights, and you're using it as some kind of precursor for freeboard, or if you're doing some kind of surface process studies, like looking at lead or flow lengths, it's a better product. It has more information, but it's not as fully developed as ATL10, which is actually getting the sea ice freeboard. So this is doing a long track flagging of surface type, especially trying to get the sea ice leads, the sea surface height, and then doing some filtering on the data to, again, get actual sea ice freeboard, not just a surface height. And so again, this is a lot lighter of a product than ATL3 or even ATL07. The disadvantages is the product isn't reported as extensively as ATL07. So things like where the ice concentration is lower, ATL07 will give you more data because we're confident in the surface heights, but not the freeboard, especially where waves could contaminate the data. Again, some of the disadvantages, some people really don't like the fact that it's a varying length scale, the retrieval. That's just how the product was developed. I would caution people on using data from the summer. Where melt ponds are present, we know there are issues with the data. We did a field campaign last year. We're working on that data, trying to improve some of the products. Again, product's been vetted, be very accurate though, especially non-summer time periods. Some people like to use the gridded products, so they want something much lighter. So that's where ATL20 comes in. So this is the gridded sea ice freeboard. So again, if you're looking for a lighter product, if you're looking to do things at, especially a monthly resolution, looking at a time series, ATL20 is a lot easier to use. And so if you're, again, looking at large scale change, like over the whole of the Arctic or the Southern Ocean, or you want to merge this with something like passive microwave products, it's a good, easy product to use for that. And then, as Tyler mentioned, the sea ice specific algorithms do pick out the leads, so where we know where the sea surface height is in sea ice cover regions. And so that's what ATL20 is geared towards, getting the sea surface height in sea ice covered regions. It is a gridded product. The advantage is, especially some of the gridded ocean products are heavily contaminated by sea ice. I would not suggest using them in sea ice covered regions right now. We are working to try to reconcile especially the ATL10 and 12 products so that ATL12 can better discriminate leads and is using the vetted product from 10 in approach to get a global sea surface height product that's reliable. But right now I would suggest, if you're interested in global sea surface height, separate out between sea ice and non-sea ice covered regions. So that's an overview of the products. I did want to talk about sort of the future of the mission. So some of the things that we did, especially in the lead up to the senior review process, which it's mostly done, but the proposal was submitted in April, presentations in June, and now we're just waiting to hear the results. But some of what we had to do for that was, show that ICESat-2 is meeting the baseline science requirements. So I listed those here. And so most of the baseline science requirements are oriented towards, accuracy of like ice sheet height change or sea ice freeboard, or also the measurement structure, like how are we spacing our tracks and such like that. So we've now found that we're able to meet all of these level 1 science requirements. We have a paper that we're preparing, myself, Tom Newman, and Lori Magruder. It's progressing, we're working on it, but yes, we can show that we're actually meeting the science requirements for the mission. But as I mentioned, we're waiting on the guidance from the senior review process. Some of what they asked us to focus on was, we are trying to repeat tracks, but we're also trying to space tracks out in the land regions, so where vegetation is. So we're trying to balance between, how can we get change detection, but then how can we just densify the tracks? And so, again, they asked us what our plan is, but in some ways this is open. We're open to feedback, like how best can we optimize the mission, especially with regard to how tracks are laid out. They asked a lot about, what kind of international collaborations we're planning. Most notably, we do work a lot with ESA. There's a lot of common overlap there. They were concerned, especially the decommissioning of Calypso, a LiDAR taking atmospheric measurements. So ICESat-2 is going to be the main game in town for that. And so we're looking at a shift in the community towards using ICESat-2. A lot of what we proposed is, developing new products, especially bathymetric products, and doing CalVal for that. This is something pretty new. It wasn't in the main science requirements for the mission. But again, as we see new science develop, we're looking to, where can we put resources for the mission to make better and new products? And then how can we continue some of the products, like the ocean products, or getting coastal altimetry? There were budget cuts to the mission, and so we had to balance between, how do those budget cuts impact the product development work? So some of the product development work is going to freeze, and we're going to bug fixes, and then some will just continue as normal. So that's sort of the mission outlook. So release 6 data is now out. We're kind of looking towards 2024 to plan the next release of data, so release 7. So, new improvements to the products. And then new science team will meet as a whole in early October. I guess one of the big things that also came out from senior review and is repeatedly asked is, how long is ICESat-2 going to last? So we, as part of the process, we did sort of an end-to-end look at, different systems on ICESat-2. What are the lifetime limiting items? The laser is extremely healthy, doesn't appear to be problematic. Right now, what we do know is it looks like, if anything, fuel would be where we would estimate, what's the end of the life for the mission. And this is just a best estimate. It's really based on what is the solar cycle going to be like, over 10 plus years. It's pretty uncertain. And so that's where we just give, what are the range of estimates? So mean nominal is somewhere around 2036 is when we would expect fuel to be done. But, we'll see what the sun does over the next several years. So,
All right. All right, one last thing before we go to lunch in our last 10 minutes is, so at ICESat-2 science team meetings, we often do a feature find where you look for cool things in ICESat-2.
Hey, Tyler, really quickly, tell us about slide rule. This will be one of the many ways we can get at ICESat-2 data.
Shouldn't hold things in my hand. I'll put it in my pocket. Slide Rule is a data as a service provider, and it not just computes ICESat-2, but it's a way of computing data in the cloud. And so it's basically meant to, you're a scientist, you have something you want to do, but you want to do something big. So if you want to process a whole bunch of ATL03 data, Slide Rule can do this for you. You don't need to download it. It has easy access to ATL03. And so what I did here is I just drew a box, and I didn't worry about parameters. I didn't do anything. I just drew it over Seattle, and we can look at the I-5 bridge and we can see the lake below it. And it's kind of funny. But we can also go to that blimp hangar in Germany and go see the bottom of the pool, because why not? But people have found, the pyramids and craters, like even things like I had what was called a Photon Friday for Mount Rainier, as we could see a lenticular cloud. And so we had the glacier and the cloud above and like the surrounding vegetation. So yeah, go find some cool stuff and post them on Slack, and we'll see what everyone finds over the course of the week. And with that, thank you all for your time. And I am happy to answer questions on ICESat-2. And we have a bunch of experts here that are product leads and just mega users, or whatever you want to say. So thanks for your time.
Yeah, Jessica just suggested a great idea. Could we identify the product leads who are in the room right now? Maybe a quick stand up or raising of hand. It's just, it's okay.
But Ben Smith works here.
Yes, okay.
Oh, and Jamie Morrison also works at UW, but he's not here. But there's a number of people here.
Yes, awesome. Any questions for Tyler and Nathan?
Rockin'. Oh, yeah.
That was a great talk. And I just wanted to ask, is there any access to these slides available if you want
They
to
are
review?
on the Jupiter book.
Okay.
For this. So if you go to the mission overview, there's download the slides, and then there's a way you can interact with this show code button, and you can dump that into a notebook that's in the same mission overview. And then a lot of the imagery that I used in the land ice slides is also in a notebook in the same thing. So yes, the slides are there for you to dig into, and they're going to be there permanently.
Okay. Thanks.
Yeah.